Good afternoon, class. We are looking at chapter 5, section 5.4, the substitution rule. Here's the first part. So we covered 5.1 to 5.3, the fundamental theorem of calculus, and now 5.4, the substitution rule. These are various integration formulas we should be very comfortable with. Here's the FTC, fundamental theorem of calculus. If f is a continuous function on the closed interval of a to b, d dx of the integral of a to a from a to x of f of t dt is f of x. This means if you integrate f of t dt from some number to x and then differentiate that, you get f of x back. Given capital F prime equals lowercase f of x, the integral of a to b f of x dx is capital F of b minus f of a. This is a definite integral and it is a number, everybody. Now this is a substitution rule. The integral of f of g of x g prime of x dx. This is the u. This entire thing is du. So it's the integral of f of u du. So integration by substitution is the reverse process of the chain rule in differentiation. Let's differentiate this. If you want to differentiate this, you get capital F prime of g of x times g prime of x. This is the chain rule. So d dx of capital F of g of x is f prime of g of x, g prime of x. Capital F prime is the same as lowercase f. Remember that generally speaking, that's what we use. So let me. Right. So lowercase f of g of x, g prime of x. So we are going to call this function the u function, therefore it's called the u substitution. If u represents g of x, then du dx is g prime and du is g prime of x dx. So the integral of f of u du is capital F of u plus c, which is capital of g of x plus c. In other words, you know how to differentiate this to get to this one. So if you integrate this one with respect, and of course you have a dx, you must get this function and a constant. So over any interval for which u equals g of x is continuously differentiable and f is continuous on the range of this function, the following relationship holds. The integral of lowercase f of g of x, g prime of x dx, where g of x is u, this entire thing g prime of x dx is du. We can call it f of u du, which becomes capital F of u plus c because we said capital F prime is lowercase f. And u is g of x, so capital F of g of x plus c. So 5.4, the substitution rule. Integration by substitution is the reverse process of the chain rule in differentiation. I want to differentiate this, and here's the tip. Look for a function u equals g of x anywhere here in the integrand, and its derivative du or g prime of x multiplied by dx. So a couple of things I want to mention here. Number one, you could raise this to the power of 3 and avoid substitution, but what if this one is like 300? Then you can't do that. So I want to go with the substitution for practice, number one. Number two, you may notice the derivative of x squared plus 5 is 2x. That's another thing you want to pay attention. But in general, when you have polynomials, the more complicated one, in this case, x squared plus 5 is a choice of you. This one is the less complicated one. Notice that if I differentiate this, du dx becomes 2x, which means du is 2x dx. So I want to pay attention to this tip. So to make sure we understand what's going on, we're going to put the 2x next to dx, and we're going to say, okay, this is u And this entire thing is du. So we are looking at the integral of u cubed du. And that follows the power rule, becomes 1/4 u to the power of 4 plus a constant. Now reverse substitution, replace the u with x squared plus 5, and you're done. All you have to do, differentiate this if you want to check, and you get this one. That means not dx, the rest of it. So you can check your work. Again, we have a similar example where we have two polynomial functions. One of them is x cubed plus 1. One of them is 3x squared. Of course, this is being raised to the power of 10, but I'm interested in x cubed plus 1. I hope you notice its derivative is 3x squared. So it becomes clear that this is the choice of u. Its derivative is 3x squared. U becomes 3x squared dx. So first, let's move things around. I'm going to put the 3x squared next to dx. So this entire thing is u, and this thing is du. Which means we have the integral of u to the power of 10. Following the power rule, we get 1/11 u to the power of 11 and a constant. Reversing the substitution, meaning u goes back to x cubed plus 1, and that's our final answer. Same situation, we are dealing with different polynomials. Clearly, this is more complicated than this one. You also notice this is the derivative of that. So let u be the first parentheses, x squared plus 3x plus 5. Its derivative is 2x plus 3. So du is 2x plus 3 times dx. So we notice this is u, x squared plus 3x plus 5. And this part, 2x plus 3 times dx, is du. So we have 9u du. Again, the power rule 9 halves u squared plus a constant, and u reverse substitution. We change it to x squared plus 3x plus 5. The final answer is 9 halves x squared plus 3x plus 5 quantity squared plus c. So in short, if you have a bunch of polynomials, the more complicated one is a choice of u. All right. So what happens when we have fractions? Now notice this is a rational function, this is not. But both of them are fractional format. So we treat them the same when we want to integrate. The very first step is, can I simplify the fraction? In this case, the answer is no. Therefore, I have to choose the denominator as a choice of u every. What is the derivative? E to the power of t. So what is du? E to the power of t dt. Now it's important to know that if you have dt, dx, d theta, it's really part of the numerator. So I'm going to rewrite this as e to the power of t dt over the denominator, 5 plus e to the power of t. If by any chance this is not in the numerator, that's wrong. Okay, that's a typo. So you have du over u. And you know the integral of 1 over x dx is ln x. So this is also ln u plus a constant. And replace the u. The final answer is natural log of absolute value of 5 plus e to the power of t plus a constant. Because this expression 5 plus e to the power of t is positive, you could change the absolute value to parentheses. It's just as good. Okay, everybody? So again, it's your choice. You could change that if you want it because the expression is positive. Now, when we go here, the very first step is to simplify. And we can't because the denominator, if you recall for the quadratic formula that has the formula ax squared plus bx plus c equal to 0, and x is minus b plus minus d squared of b squared minus 4ac over 2a, b squared minus 4ac is called the discriminant. When it's positive, you have two distinct real solutions. If it's 0, you have one real solution. If it's less than 0, there is no real solution or two complex solutions. If b squared minus 4ac is a perfect square, then this expression ax squared plus bx plus c can be factored. So you have to realize, if I were to write the information for this, I'm going to write it here and I'm going to erase it. A is 1, B is 2, C is negative 1. So B squared minus 4AC. You get 8. 8 is not a perfect square, cannot be factored. And by the way, even if we could, we should have a factor of x plus 1 to simplify, otherwise it doesn't do us any good. So the denominator is a choice of u. If I differentiate this, I get 2x plus 2. Du dx is 2x plus 2, or 2 times x plus 1. So what is du? Same thing times dx. And I factor the 2 out. You'll see in a moment why it's important. 2 times x plus 1 times dx. So I'm going to put the dx next to x plus 1. And when you compare and contrast, you notice that the denominator is u, but the numerator is not du because number 2 is missing. Now, in most texts, including yours, they do solve for dx. You can go that route. But here's the easier way. Because a number is missing, I can put the number here and undo it with its reciprocal, which is 1/2. You can only do this if a missing thing is a number. For example, it's 5 you put 1/5. Is -2, you put -1/2. The reciprocal of a positive is positive, the reciprocal of a negative is negative. Now the numerator is du, the bottom is u, and you can see the same thing. So this part becomes a natural log. So 1/2 ln of absolute value of u and a constant. This 1/2 doesn't go away, and u is replaced. So you get 1/2 natural log of absolute value of x squared plus 2x minus 1 plus a constant. You must keep the absolute values because this expression can be positive or negative. So you can't lose the absolute value sign. I can't emphasize this enough, everybody. Whereas here, because the expression is positive, you could lose the absolute value sign. It's not a big deal. Now, let me erase my work. What if we had the reciprocal of this one? We have to do long division or synthetic division because the degree would be larger for the numerator. I'm going to look at the reciprocal of this one. So that means this part is 5. Where's the difference? This is 5 e to the power minus t. This is 1. And I don't need a substitution. The answer is minus 5 e to the power minus t. This is t and a constant, and you're done. So compare and contrast. We must use a substitution. We don't need a substitution in this example. All right, what happens when we are dealing with exponentials? In that case, the exponent is a choice of u. So take the derivative, you get 5x to the power of 4. Du becomes 5x to the power of 4 dx. We are going to move this next to dx so it becomes clear that we have e to the power of u du. This entire thing is du. And the answer is itself. E to the power of u and a constant. Replace the u. You're done. This is a similar question. X to the power of 4, e to the power of x to the power of 5 minus 2 dx. When I take the integral again, since you're dealing with the exponential, the exponent is a choice of u. If I differentiate this, I get 5x to the power of 4 again. So du is the same thing, 5x to the power of 4 dx. So again, just like here, we are moving x to the power of 4 so it becomes clear what we have and what's missing. So over here, 5 is missing. And because it's a number, you can put the number in here and undo it with its reciprocal. You can't do it if it's a variable class. Again, in some text, in most, they solve for dx. But what I'm telling you, what I'm offering you is an easier way. Plug in 5, undo it with 1/5. Now, this is e to the power of u du. This is the same as this, e to the power of u and a constant. Don't forget the 1/5. And replace the u with x to the power of 5 minus 2. The final answer is 1/5 e to the power of x to the power of 5 minus 2 plus a constant. If you differentiate this, will give you the same expression without the dx.